going to give you a quick review for previous class. For heterogeneous reactions, which is more than there are two or more phases of reactants or products involved in this heterogeneous chemical reaction. So in order to get or obtain the overall rate equation, we must consider the phase-to-phase mass transport part and also the chemical reaction kinetics. For example, that if we have a chemical equations is solid carbon react with gas oxygen, then generate the gas carbon dioxide. In this case, we know that this is a heterogeneous reactions because the phases, there are two phases involved in these chemical equations. And so in this case, we need to consider the mass transport between two phases. Here it means you need to consider the oxygen molecules, how fast the oxygen molecule be transported to the surface of solid carbon and start the chemical reactions. So in order to obtain the overall rate equation, this overall rate equation can be simply classified into three steps. The first one is the mass transport of oxygen to the surface of the particle. Then this oxygen will start the chemical reaction with the solid carbon. The last one will be the mass transport of the carbon dioxide out of the surface. So usually, in order to simplify this heterogeneous chemical reaction, we always assume the product carbon dioxide can easily get out of the surface of the carbon. So this direction is irreversible reactions. So here, what's the purpose here? We need to model or reconstruct this heterogeneous chemical reaction. So how to do that? How to model this heterogeneous reaction, including the mass transport part and the reaction part. And relationship between both this one is in series reactions, right? So we can use the concept we learned from the electrical circuit. V equals to IR. When we apply a battery on this circuit, then we will drive the current passing through each electrical component with individual resistance. So here, we also have a driving force, which is the concentration gradient. Here is the concentration of the oxygen, concentration gradient of the oxygen, and it will drive the flux of the oxygen passing through each different layers or different process involve the transport in the film layer and also the reaction at the surface of a carbon. So each one you can consider also this resistance. So we have a resistance of the transport and also a resistance of reactions itself. Okay. So in order to confirm whether we can use this electrical circuit concept learned from electrical circuit to apply on this heterogeneous chemical reaction. So we give you an example. Here is a liquid-solid reactions. It is a heterogeneous chemical reaction. So we have a liquid A react with solid B and generate the liquid R. Then we also assume the liquid R can easily get out of the surface of a solid B. So here, we try to plot the concentration of reactant A in blue. So we got the CaL in the liquid main body will keep uniform. In the liquid main body, the concentration of reactant A keep constant. But when the molecular A or reactant A is going to transport or diffuse through this liquid film layer, so the concentration will decrease as a function of location. And when it arrives the surface of the solid B, then will start this chemical reaction, will react with reactant B, and this chemical reaction will come. We assume this chemical the reactant A will be consumed completely, so the concentration will drop to 0 at the surface of solid B. So we can formulate, as we learned previous, right? Probably the driving force will be the concentration gradient of reactant A. And here we can easily formulate the flux passing through this whole path, right? Including the mass transport part and the reaction part. So when you try to write down the flux of reactant A passing through liquid film layer, will be the consumption rate of reactant A per interfacial area. So, but this area obey the fixed first law, so minus diffusivity concentration gradient. So you got the concentration gradient CAS minus CALO divided by the thickness of this film layer, delta X. So after arrangement or organize them, then we also lent this as a spatial term we call a transport coefficient, diffusivity divided by the thickness of the liquid film layer. So this we call a KL is the transport coefficient inside the liquid film layer. And so here we know as long as you have the higher transport coefficient, that means the diffusivity is higher. That means the A can diffuse faster or be transport faster in this liquid film. Okay, so first of all, you can successfully formulate the flux of reactant A passing through this liquid film. Then let's try to write down the reaction rate at the surface. So it would be minus R double prime. Double prime means what? Is a per interfacial reaction area, right? So we assume it is a first order reaction. So K double prime CAS minus 0 because the reactant AB consumed completely. So you got a CAS minus 0. Okay, so if it is a state reach the steady state, means the supply of reactant A will be equals to consumption of a reactant A. So we got this relationship. So we get what CAS can express like in terms of a CALO. Why we need to make this kind of assumption to reach the steady state? Because if the purpose here is write down the consumption rate of reactant A, right? Usually people will just directly write it down as a K double prime CAS. But however, it's very difficult to scientists to measure the CAS, means the reactant concentration of reactant A at the surface of solid B is unmeasurable. So we make this assumption, then we can substitute CAS in terms of CALO, which is measurable, because CALO is a concentration of reactant A in the liquid main body. So we substitute CAS in terms of CALO, then we will get a consumption rate of reactant A expressed like this. And you divided the K double prime and KL on both sides, then you will get this results, right? And what we have here is this is a flux, right? Flux, the flux of consumption rate of reactant A per interfacial area. So you can consider this is a V equals to I R is a total resistance. V is a driving force. Here, driving force you can consider as the concentration gradient is a CALO or concentration difference. So CALO minus 0, and the flux is passing through whole this process. So it's a flux consumption rate of reactant A, and this flux passing two different layers. The first one is the transport, and second one is reaction. So this is the reactance, resistance of mass transport and resistance for chemical reactions. So here, if you consider this is the resistance of mass transport, so it's reasonable, right? Because it is a reciprocal of transport coefficient. We let it as a resistance of mass transport. If you have a higher transport coefficient, that means the resistance is slow. So we use a reciprocal of transport coefficient serving as a resistance. And here the same idea is a rate constant, rate coefficient. So reciprocal of rate coefficient, we use it as a resistance of chemical reaction. Okay, so if you write it down, you will get this one, right? So as I show you, if we use this electrical circuit as our model, then you will find that the driving force will be the concentration difference at the two ends, okay, CAL minus 0. And passing this path included the mass transport part and also the reactions part. So we got the same flux of reactant A, and passing the first one is a mass transport in liquid film, and the second process will be the chemical reaction at the surface of solid B, and resistance is reciprocal of transport coefficient or reciprocal of the rate coefficient, reaction rate coefficient. So some people will write it down expressed like this. So it's a total resistance included the transport part and also the chemical reaction parts. Okay, so this is what we learned or what we told you in previous class. So today we are going to move forward. Then I will give you the other example. And this example will be the gas, liquid, solid reactions. Gas, liquid, solid reactions. So also you can observe we have more phases involved in this reaction. So definitely this is heterogeneous chemical reaction. So in this kind of case, you need to consider what? You need to find out the driving force, the flux passing through each layers and steps, right? Okay, so in what kind of situation that will belongs to gas, liquid, solid reactions? So here what we give to you is we have a pure gas reactant. It's bubbling through liquid containing suspended catalyst particle in a slurry reactors. So what we have is we have a liquid, and reactant A, gas A, is bubbling through this liquid, and inside this liquid we have the catalyst particle. Okay, so the reaction will be happen in this region. You can expect the reactant A is going to diffuse through this liquid, then arrive at the surface of the particle, catalyst particle, to be catalyzed, right? Okay, so we try to enlarge this region and draw these figures and try to find out what's the driving force here and the flux and how many layers the flux of reactant be passed through or react with. So we got the reactant gas A and also catalyst solid particle here, and in the middle we have the liquid in the middle. Liquid. So we write down main body, liquid main body. And as we mentioned, if we have two different phases, in between there exists a film layer. So in between the gas and liquid main body, we have a film layer we call a gas film layer. And in between the liquid and the solid catalyst solid particle, we have a film layer we call it a liquid film layer. Okay, and we write down the gas concentration of reactant A in gas phase. Because we know the concentration, we call it a CAI here. And the reactant A is going to diffuse through this gas film. So we got the transport coefficient equals diffusivity of reactant A divided by the thickness of this gas phase layer. We call it a KL1. And then the reactant A is going to diffuse through this main body. And here, we write down the concentration, keep uniform here. So that means we make a very important assumption is there's no resistance exist in this liquid main body. That means the transport coefficient is very, very fast or very, very large. So reciprocal of infinity, you got the 0. 0 means the resistance equals to 0. Then the reactant is going to diffuse through the liquid film layer, and you can observe the concentration decrease as a function of location. And also we have a transport coefficient KL2 equals to diffusivity of reactant A divided by the thickness, diffusivity of reactant A passing through this liquid film layer divided by the thickness of this liquid film. Okay, then next you got the reaction happen at the surface of this solid or catalyst. Okay, so we'll try to write down the flux because we got, as long as let's reach the steady state, the flux equals to constant. Okay, so we try to write down the flux of reactant A passing through this gas phase. So we got the transport coefficient times CAI minus CAL. Okay, so this is what we got, or what we learned from previous slide. And CAL is also transport coefficient KL2 times CAL minus CAS. Okay, and JR, yes, we also assume is complete consumption of reactant A at the surface of this catalyst or this solid particle. So we also assume it is a first order reaction. So it's a K double prime CAS minus 0. So you got the third equation. Okay, so usually, as we mentioned, the purpose to solve this heterogeneous chemical reaction will be formulate the consumption rate of reactant A, right? In the beginning, you will write it down as like this. But as we mentioned, it's very difficult to scientists to measure the CAS. It's a concentration of reactant A on the surface of this catalyst. It's very difficult to measure the concentration of reactant A at the surface of this particle, right? So we have this equations, these three equations, so we can substitute CAS in terms of CAL. What's the CAL? Is a concentration reactant A in the liquid, but it's still very difficult to measure, right? So we substitute this one. So it's still very difficult to measure CAL, so we use the equation 1, 2, 4, then we can get CAL, we can substitute CAL in terms of CAI. So now CAI is measurable because it is a concentration reactant A, right? Okay, so finally we can get the consumption of reactant A expressed in terms of CAI. Then after arrangement, we find that it can be the bottom part included three terms. The first one, and the first term is the reciprocal of KL1. It's a resistance of the gas phase, resistance of liquid phase, and resistance of reaction. So it's similar. You have a series reaction involve the transport resistance, and reaction resistance, and they are series reactions. So you plus all the resistance together, sum them up. So you have driving force, flux times total resistance. Okay, so K over rho, so total resistance included 1, 2, and 3 steps. Okay, so by using this, by these examples, we can confirm. I believe, as long as you as long as you draw the pictures which is fit to what you are dealing with, then you can easily write down the consumption rate of reactants equals to the driving force here is a concentration difference and also the resistance. Some people will ask, yes, professor, you miss one term here, resistance here. Yes, as we mentioned, resistance, transport coefficient in this liquid main body, we assume is very fast. Transport coefficient is approach infinity, so reciprocal of infinity is plus 0, so we can ignore that term here. Okay, so you can, as long as you draw these pictures, I believe you can simply write down the consumption rate of reactant A expressed as driving force and total resistance, included each layer's transport and reactions. Okay, so before we ended this fluid-solid reaction, we are going to give you an example to show you how to measure or estimate the thickness of the silicon dioxide. Okay, so this example is the oxidation of silicon substrate. How to grow the silicon dioxide layer on the silicon substrate in the semiconductor industry. So here we provided you two different methods. The first one we call it the dry method, which is like you have a silicon substrate, right? You put it into the oven, then you flow the oxygen at a high temperature, 900 to 1200 degrees C, then you will get a silicon dioxide layer. This is what we call a dry method. And the second method we call is a wet method. Yes, you also put the silicon substrate into the oven, then but you flow the water vapor, then you will get the silicon dioxide and also have a hydrogen as a product. Which method can have a faster growth rate to get the silicon dioxide layer? And also, how can you estimate the growth rate for each different method? Growth rate of the silicon dioxide for dry method and also the wet method. So this is the question. So you need to calculate the growth rate of silicon dioxide and answer me which one have a higher growth rate and why. So in order to answer these questions, first of all, also you need to write down. You need to draw what you're dealing with. So we use a dry method. Silicon substrate react with the gas oxygen as an example here. So in beginning, what we have is we have a silicon substrate here, x equals to 0. So this is the surface of the silicon substrate, and we have oxygen. So we have the gas oxygen here, and also we mentioned because gas react with the solid phase. So in between we have a film layer. Here is a gas film layer. So when you try to draw the concentration of oxygen, here we try to draw it. Okay, in the gas phase we know the concentration is here of the oxygen, and oxygen is going to diffuse through the gas film to reach the surface of the silicon substrate, and we use the Cs to represent the concentration of oxygen at the surface of the silicon substrate. And then what? This is at T time 0, right before the chemical reaction happens, right? But next, if you try to heat this up, you try to, if this reaction starts, then you know the oxide layer is going to get thicker and thicker. So you can observe the thickness of the oxide layer becomes to delta. So with increasing time, you can observe the silicon dioxide layer will get thicker and thicker to reach the thickness of delta, right? But here, if you want to draw the concentration of oxygen, we will write it down as a CS prime. This is oxide layer, right? CS prime, what's a CS prime? It's the solubility of the oxygen into the oxide layer. And within this layer, also, the oxygen is going to diffuse through this oxide layer to reach the surface of the silicon substrate and continue oxidation steps. Okay, so what you have here, as long as you draw this one, then we can have the flux, right? So what we have is we have the flux of the transport of the oxygen in the gas phase. Then we also have a flux of oxygen in this oxide layer, and also the reaction of the oxygen with the silicon substrate, right? So first of all, we can write down the transport in the gas phase. So how to formulate that is the transport coefficient times the C infinity minus Cs, right? And you also this is we use the oxygen as an example, but also you can substitute with the water vapor. It's the same idea. Just rename it gas as oxygen, gas substitute gas as water vapor, but all other things, and this will become the concentration of water vapor, and also the concentration of water vapor at the surface of silicon substrate. But you use the same equation, right? But just different terms, okay? So next, we are going to try to formulate the JD. JD, what's the JD? Is the transport of the oxygen into the oxide layer, so will be the transport coefficient times Cs prime minus Ci. This is a concentration of oxygen at the silicon substrate, at the surface of a silicon substrate. Okay, but transport coefficient, we didn't use the we didn't assign a K transport specific K transport coefficient to here, but we use the diffusivity over delta, is the thickness of the oxide layer here, instead of using a specific K, because during the reactions, the thickness delta will increase with reaction time. So we cannot assign just a specific K, specific value of K to here. So we use the diffusivity over delta, because delta is going to increase with reaction time. And also next we try to formulate the reaction. Would be, we assume it is a first order reaction, so Kr rate coefficient times the Ci, and we assume this concentration of oxygen will be consumed completely, so Ci minus 0. So as long as it reaches steady state, we know Jg equals to Jd equals to Jr. That's what we learned from previous slide, right? And next is very important. This is a very important process, is a transport in oxygen, the oxide layer, because you can expect it. This step will be changed with time, because the delta is changed. The delta is increased over time, and as you expected, if the reaction is in the short time, that means reaction in the short time, in the beginning, the delta is very thin, right? So oxygen is easy to react with silicon, but with increasing time, you can observe the thickness of the oxide layer. It gets thicker and thicker, so that will be difficult to oxygen to be transported to reach the surface of the silicon substrate. So for longer reaction time, you observe the thickness of the oxide layer increase. So definitely it's very difficult to oxygen that will spend more time to allow the oxygen be transported to arrive the surface of the silicon substrate. So as you know, we believe for longer time diffusion, this step probably will be the rate limited step, right? Because this step is very slow, because the thickness of the oxide layer will get thicker and thicker. Then that will takes more time to allow the oxygen be transported to the surface of silicon substrate. But for a shorter time, this step probably would not be the limited step, because because the thickness of the oxide layer is very thin, right? Okay, so in order to confirm what we get, this is some just it's not quantitatively description, just what we learn from this these figures. This is just some idea. But in order to quantitatively to get the rate limited steps for short or longer time, we need to do is we need to make some assumption to simplify all the situations. So the first assumption, the very important assumption is we assume Km is a transport coefficient in the gas bin. It's very high. So transport is very high. Km is very high means transport is very fast. So no gas bin resistance. And also we also assume there's no interfacial resistance at x equals to 0. So that means C infinity equals to Cs equals Cs prime. So we make this important assumption to simplify the situation we deal with. So now you only need to deal with this JD equals to JR. So we try to formulate JD equals to JR. So JD is expressed like this. And don't forget, JD is the diffusivity divided by delta. Delta will change with time, okay? And KR here. So based on this, what we learn, this equation, what we learn, we can use a CI expressed in terms of CS, because as we mentioned, CI is not easy to measure, right? So, and next, don't forget, what you learn is you can formulate the consumption rate of reactant, consumption rate of oxygen, right? But it's still very difficult to use. There's still missing link with the flux of oxygen with the thickness of oxide layer, which you can measure that. It's a measurable oxide layer. It's still a missing link. So so we try to find out what's the missing link between oxygen, flux of the reactant oxygen with the thickness of the dioxide layer. So here we try to find that J oxygen is a consumption of oxygen, is a JD and JR, right? And what's the consumption of oxygen? We can use the D delta is the thickness of the increase, smallly increase of the thickness of dioxide layer, times A is area, interfacial area. So total is what? The volume. This is the thickness, and times the A is the volume of oxide layer, right? The volume. So you times the density of the oxide. So you got the total weight of oxide. Then you divide it by the mass of the total weight, right? And the mass of oxide formed by one molecule. So you will get how many molecular oxygen be consumed for form this weight of oxide. So this is how many molecular per unit time per area. So this is a flux of oxygen, right? So based on this, you successfully to link the J oxygen with delta. It's a thickness, a measurable thickness of oxide layer. Then next, this is a J, R and JD. So you drop this term out, then you can write this down here. You have get the J oxygen. And next, we are going to CI is very difficult to measure, so we substitute CI in terms of CS. So you got KR times this term, and you just after arrangement you got this result. Then next, just just arrange it, and we substitute KD. We use the D. KD, what's the KD is diffusivity divided by delta. So we will get this equation. And we move the dt to one end and d delta to the other end. Then we take the integral on both sides For t is integral from 0 to t, and delta will be integral from delta I from delta. Delta I is because silicon substrate always have a very thin native oxide before reaction. So the thickness of for the native oxide on the silicon substrate always is like several angstrom. So we use that as a delta I, that before reaction happens, there's already exists a thin layer of native oxide on the silicon substrate. So we call this a delta I. So we have these equations. And after arrangement, you can use this equation to substitute this equation, and A is equals to this, and B is equals to this, and tau is equals to this. And this is easy to get the delta, right? Because you can use this solution, then you can successfully get this delta. And delta A, you can use the A, B, and tau is like this. Okay, so now delta is the thickness of oxide layer. This is measurable. Okay, so we just copy what we learned, what we get from previous slide. So based on this, you know what? Based on this solution, delta is a measurable oxide thickness of oxide layer. So, and you find this you can find this T plus tau. If T plus tau is very, very small, smaller than A squared over 4B, that means this term is very, very small, right? If this term is very small, 1 plus this very small term and together to 1 over 2, this is very small, then you will get what? If you got the 1 plus x and 1 over 2, and if x is very small, then this is can be, you can use 1 plus 1 over 2 x, right? And you also minus 1, so you got is 1 over 2 x is this term, 1 over 2x. So if for short reaction time, then you will get this results, right? To A over 2 and 1 plus 1 over 2x and minus 1. And this, you can just turn this, drop this turn out 4. And this A, drop 1A. So you got a B over A, T plus tau. And what's the B and A? B here over A. So you got the KRCSM over low T plus tau. CS is a surface concentration, it's a constant. M is a molecular weight. Low is a density. So actually, you can know that the delta, thickness of oxide layer, is proportion to Ki, is a rate constant of this reaction. And the rest of part actually is the constant, right? You know that, right? So it's a constant. So this is, some people call it, for a short reaction time is reaction control, because the thickness of oxide layer is proportion to rate constant, Kr. And for a longer reaction time means this is much larger than A squared over 4B. This term is very large, so you can drop this term out, and this will take the square root it. So you got the 2. And B, you still have it, and you drop this term out, right? And this will be square root of B, T plus tau, and square root of B, T, because T plus tau is very large, and tau, and also we assume T larger than tau, right? So you will get this one. And what's the square root of B? B is here, right? So square root of B similar to square root of D, diffusivity. Diffusivity means the diffusivity of oxygen into the oxide layer. So it's a diffusion control for longer reaction time. So when you try to write down the thickness versus the time, reaction time, for a short reaction time, for short time reaction time, you find that delta is proportion to, is linear proportion to t, and the slope is b over a, right? And this term is proportion to kr, rate constant. And for a longer period, show a reaction time, that will becomes to proportion to square root of diffusivity, right? So some people call this regime is a linear rate constant, and this is a parabolic constant. Just let you know, some people call this regime is a linear, and this is a parabolic rate constant. Okay, so this regime, you know, the delta is proportion to kr, rate constant. Don't forget what's inside, what's the rate constant, what parameter will affect the rate constant. For rate constant, there's an exponential term embedded inside, right? Included the exponential, included the activation energy, and the T, working temperature, right? So for shorter reaction time, if we measure, for example, if you measure the thickness, and I can use the other color. If you measure the delta thickness as a function of as a function of reaction time, and for a short reaction time at different temperature. For example, like this is a T1, right? Then you got this value, and if you try to decrease the temperature, probably you will got, and you measure this one, probably you will got this one. Decrease the temperature, then you also measure the delta, the thickness for a shorter reaction time, then you got this slope, right? And after fitting, you slope, you probably got this T2, and probably T3, decreasing on T3. Then after fitting, this slope will be log this one, log kr, similar to the slope will be belongs to activation energy, right? Because you use log b over a versus 1 over t. And this term actually included a kr. If you log kr and versus 1 over t, then slope will be what? Minus activation energy divided by k, right? So you can get the activation energy. So you can do that for the dry method, and also can perform that for water vapor. So you also will get this slope. So after fitting, you will get activation energy for water vapor for the dry method. So for short reaction time, which is we call a reaction control. In this case, we find that wet method, and no matter it's wet method or dry method or wet method, they have the similar activation energy, right? So that means this for shorter reaction time, for short time, actually is reaction control. That means you also get the similar activation energy. That means no matter you use a dry method or wet method, the reaction part, the reaction energy barrier is similar. Is that reasonable? Yes, because silicon, it was silicon bond, right? Silicon bond on the inside the silicon substrate. You want to convert it silicon bond to, you want to convert the silicon to become a silicon dioxide layer. That means you need to break silicon bond, right? So you need to break a silicon bond. That tell you what this energy is similar. Yes, it's similar. The energy barrier is similar because reaction control. In order to allow silicon substrate to become an oxide layer, first of all, you need to break the silicon bond, so the energy is similar. But for longer time period, that becomes the diffusion control. So you also can do the same thing. Is like when you can measure the thickness of the oxide layer for longer time, and you got the slope here, and you take the log B and 1/T, and as you know, what's inside the facility? Embedded the activation energy, exponential activation minus activation energy times the KT, right? This is exponential, right? This is exponential. So you log this value 1/T, then slope will be minus activation energy divided by K. Then yes, do the same thing. We can measure the thickness of oxide layer at different working temperature. We got the T1, T2, and T3. And for T1, you have you know the log B, and T2 you know the log B2, log T3 you know the log B3. Then after fitting, you know the activation energy. The same thing you can apply for the water vapor. Then results come out, the activation energy for water vapor is smaller than the oxygen. What that means? So the activation energy here for long time is diffusion control. That means the oxygen diffuse into the oxide layer with a higher energy barrier compared to the water vapor diffuse into the oxide layer. So that also tell you the diffusivity of the water vapor into the oxide layer is faster than the oxygen diffuse into the oxide layer. So definitely for long reaction time or longer processing time, the growth rate by using the wet method will be faster than by using the dry method. So for short time, there's no difference between dry method and wet method, because for short time actually is reaction control. The energy barrier, the energy to break the silicon bond are the similar, no matter is it for by using which method. But for longer time, which is diffusion control, so that will involve which molecular diffuse into oxide layer will be faster. So water vapor diffuse into oxide layer with lower energy barrier, and that means that will diffuse faster. So that will result the higher growth rate of oxide layer on the silicon substrate for using the wet method. Okay, so I'm going to give you a summary for this first part. The transport coefficient, we introduce your new term, which we call a transport coefficient. K equals to diffusivity divided by the thickness of the film layer. Okay, so we call it a transport coefficient. As long as you have a higher transport coefficient, that means the molecular is be transport diffuse faster in that specific layer. And we also show you the overall resistance is a sum of the resistance of each layers or each process. T is a transport reaction. So how to formulate the resistance for mass transport is a reciprocal of transport coefficient, reciprocal of transport coefficient in that layer, and reciprocal of rate coefficient for reactions. And how to successfully get or formulate the consumption rate for heterogeneous chemical reaction, we use a very important assumption is under steady state, we use the transport flux equals to reaction flux. Then we can successfully get the consumption rate for heterogeneous chemical reactions. And we use the last part is regarding to time dependence of thickness of oxide layer. For shorter time, then we find the thickness of oxide layer is proportion to the rate constant Kr. And for longer time, we find the delta is proportion, the thickness of oxide layer is proportion to square root of diffusivity. So for this one, proportion to Kr, we call it is a reaction control. For this one, we call it, because it's square root of diffusivity, we call it a diffusion control. Okay? So we also tell you delta is, we can measure that doing our experiments, right? And how to measure that? People usually will do that. They will perform the experiments like for different time points. Then they will get the delta as a function of t, these curves. So usually people how to get these curves, then they will perform these experiments at different time points and to get these curves, how the delta as a function of t. So that's the people usually do that. So usually like they will perform at like 30 minutes. So they will have less sample and cut it down and measure the thickness of oxide layer by either SEM by cross section or TEM by cross sectional view. Okay.